Okay, we're starting with part 2 of chapter 1, Dr. Sadin's class, Organic Chemistry 1. In this part, we're going to talk about hybridization, which is derived from valence bond theory. Now, I'm sure you guys remember a lot of things from General Chemistry 1, but we're going to talk about it again in this part. So let's start with an example of carbon. The carbon electron configuration is helium 2s2 2p2. And you see, carbon has 4 valence electrons. Now we're going to draw it in its orbitals. As you remember, S had 1 orbital and P had 3 orbitals. We're going to draw it. Now as you see, S orbital has 2 electrons, so we're going to put 2 arrows in it, opposite directions basically. And we have 3 orbitals in our P shell, and 2 of them will be filled each with 1 electron, same direction. So as you see here, the S orbital is already filled, and we have only 2 electrons available for bonding. But that is not the case. If you remember in part 1, I told you carbon has 4 valence electrons, all of them available for making bonds. So why do we have 2 here? That means one of the electrons in the S orbital will be transferred to the last P orbital, which is empty. Therefore, we're going to have 1 electron in each of these orbitals, all available for making a bond. So now that we have 1 electron in each of these orbitals, so as you see here, we're going to have 1 electron in each orbital, S1, P3. Now if you remember from General Chemistry 1, the P shell has 3 directions, 3 orbitals with 3 different directions. One is horizontal, which is the x-axis, one is the y-axis, and one is a z, which is the 3rd dimension. And the angle between each of them is 90 degrees. But in part 1, we said tetrahedral has the bond angle of 109.5 degrees. How is that possible then? Well, that means in this part, we're going to fuse S and P together, and we're going to call each of that orbitals sp3. Okay, so now we're going to draw the C atom here, ready for making single bonds. So if you remember, S had like sphere form of orbital, P had 3 dumbbell-shaped orbitals. Now, if you fuse S and P, it's going to be a little bit stretched. So this is how we draw it. We have 4 sp3s. We're going to draw them, as you remember, in a form of tetrahedral because it has 4 single electrons available for making a single bond. So it's going to be around 109.5 degrees again. So we're going to draw it like this. And each of these is basically, as you remember, I said, is sp3. Let's assume we're going to have each of these electrons bond with an electron from hydrogen. So hydrogen, as you remember, is 1s1. So it's just 1s orbital, which is in a form of a sphere. And we're going to draw circles on the tip of each of these sp3s. And as you see, the bond between each of these is called sigma bond, which we're drawing with the pink. And as I said, these circles are all each s. They're not sp3 because we only have 1 electron and 1 orbital overall in our hydrogen. So as you see, the bond between S and sp3 is called a sigma bond. We draw a sigma like this, an O with a little bit of line on top of it. So we call this sigma bond. Another type of bond that we have, and we're going to talk about it later, is called pi bond. But for now, this is sigma bond that we show here. So the definition of sigma bond is axial overlap of 2 orbitals directly with each other. And this is the strongest type of bond. The other type, as I told you, is pi bond, and we're going to show it to you later. This type of bond is the strongest because it's the axial overlap, while pi bond in the future, as you see, is going to be a side-by-side overlap. So now we're going to draw the structure of CH4 again, the 3D version of it. So as you see here, we draw one H on top, one H on the side. Now, the hydrogen that is going inside the page, we show it with hash. The one that is coming outside, we show it with a wedge, which is like a black triangle, as you see. So the bond between the hydrogen and the carbon is called sp3-s overlap. And why is it? Because the carbon has 4 orbitals, which are each are sp3, and hydrogen has only 1 s orbital, and as they share electron, we just call it sp3-s overlap. And as you remember, it is a sigma bond, so it's axial overlap. And as you see, the angle between each bond is 109.5 degrees, as it is always in tetrahedral. So here let's try attaching 2 carbons with 6 hydrogens to each other, which is basically ethane. This time, as you see, we're going to have 2 sp3s getting fused to each other. and it's going to make a sigma bond as well. But this one is going to be an sp3 overlap. It's involving two sp3 orbitals. And as you see, we're going to attach the 6 hydrogens on each sp3 of each of these carbons, which is left. And this is still an sp3s overlap, as you remember in the last example. Okay, we're going to do the next example, having two CH2s fused with each other with a double bond, which is called ethene C2H4. And as you see here, between the carbons, there is a double bond. As you remember, the bond between the hydrogen and carbon is sigma bond. And last time we had a sigma bond between two carbons. Now there is one bond left in that double bond. We call that a pi bond. Now what you need to know about pi bond is, first of all, it is not as strong as a sigma bond because it's not an axial overlap. Now for you to better understand, I'm going to draw the whole shape again. We already have it. As you see, the sigma bond is visible between the two carbons, and the pi bond is not really directly fused, so the orbitals are actually making this connection at their own central atom, and it's basically called a side-by-side overlap. As you see, if any of these carbons twist, the pi bond is broken, but the axial overlap, which is a sigma bond, is going to be intact. And as you see, these are overlapping side by side, not with a very strong connection. So as you see, the blue part is one bond of the double bond that we have between the two carbons, and we're labeling it with pi bond. So we're going to draw the configuration of carbon again, which is one s orbital with 3 p orbitals attached to each other. Now this time, the s orbital and 2 of the p orbitals are going to get fused to each other, and one of the p orbitals are going to remain intact. And that is the pi bond that we have. So as you see, we're going to draw these 3 together. And this time, since we have 2 p's attached to an s, we're going to call it sp2. And as you see, the p orbital is going to remain intact. It's not going to be fused. And it's not going to be hybridized if they ask you. So the pi bonds, as you see here, as we call it side-by-side overlap, they should be parallel to each other. And also, they cannot have like different angles as you see with the other sigma bonds. These should be exactly parallel to each other and perpendicular to the other bond, to the main bond, which is a sigma bond between these two carbons. Okay, so in this example, we're going to go after ethine. So as you remember, ethine has a triple bond between the two carbons. So it's C2H2. And we're going to identify what each bond is, first of all. The bond between the hydrogen and the carbon is always a sigma bond. And you always go after identifying pi bonds once you find out like there's already one sigma bond between the two atoms. So if you have triple bond or a double bond, you're absolutely sure that you're going to have a sigma bond between these two atoms. Then you're going to identify the rest with pi bond. So as you see, we have triple bond here. One of them is definitely a sigma bond that we're going to show it with pink. The other two, on the other hand, are called pi bonds. We're going to identify them with blue. So we're going to draw the shape right now for C2H2. You see, we're going to have 3 sigma bonds as always, and we're going to draw them with pink again. And we're going to draw the pi bonds in the shape of dumbbell. And the reason for that is because the pi bonds are exactly p orbitals, as we talked about in General Chemistry 1. The s orbital is in the form of a sphere, and the p orbital is in the form of a dumbbell. So we don't think of it as sp or sp2 or sp3. So as we draw the pi bonds, they should be exactly perpendicular to each other and the sigma bonds around them. So it's like a cross, as you see, and they have a side-by-side overlap as I'm drawing it for you. So we could say one of these p orbitals is the y-axis p, the other one is a z-axis p. Okay, let's draw the configuration again. So we had one s and 3 p's. This time, since we have 2 pi bonds, we're going to leave 2 p orbitals intact. And we're going to consider the s and 1 p to be fused with each other. And this time we're going to call it sp because there is 1 p orbital and only 1 s orbital. So it's going to be sp. The other two we're just going to call them p because they're intact and pure. And we're going to leave them like that. So in order to identify the hybridization of each atom in a full molecule, what you need to consider is the number of sigma bonds. So if a carbon or any other atom, if they have only single bonds around them, like 4 single bonds around them, that means there are 4 sigma bonds. So there is no p orbital hanging there. So basically it is sp3. Now, if, like the second example, if you have one double bond and two single bonds, the double bond only has one sigma bond. So basically we have two from the single bonds and one from the double bond, sp2. And if you have a triple bond and a single bond, you're going to have sp, because you're going to deduct two p's from the sp3 because those two p's are remained intact and they're not hybridized. So it's just going to be sp. So here we're going to sort the numbered bonds from the shortest to longest. As you see, they've already given us the molecular formula. So we're going to draw the Lewis structure. So it's CH3, CH, double bond CH, CH2, C, triple bond CH. So as you remember, I told you, always try to start with the carbon chain. Then you can add up the hydrogens as you want. So C, single bond C, double bond C, single bond C, single bond C, triple bond C. Now we're going to add the hydrogens around. Now as you see, as it is labeled, the number 1 is the bond between the hydrogen and the carbon on the far left. The carbon only has single bonds around it. So as you see, the hybridization is sp3 for that. The second one is the bond between hydrogen and the carbon on the second one, which already has one double bond with the carbon on its right side. The third one is the bond between the hydrogen and the carbon, which has all single bonds. And the fourth is the bond between the hydrogen and the carbon that has a triple bond with the carbon on its left side. So as I said, the first thing we do is to identify the sigma bonds. Then we're going to go with identifying the pi bonds. So all the single bonds are sigma bond. All the ones including hydrogen, and one bond of either a double bond or a triple bond. Anything left in the double bond and the triple bond is going to be considered a pi bond. So we have one in the double bond and two pi bonds in a triple bond. So now we're going to identify the hybridization of each of these. The first carbon, it has 4 single bonds around it and 4 sigma bonds, so it's sp3. The second carbon has 3 sigma bonds, so it's sp2. The third carbon, the same story. Now, the fourth carbon is sp3 again because it has 4 single bonds around it. The fifth one and the sixth one, since they have a triple bond between them, they're going to be left with 2 sigma bonds around each of them. So basically they're both sp. Now in order to sort from shortest to longest, what we need to know is to understand when there is a carbon with a triple bond on the other side and a hydrogen on one side, because there are 2 pi bonds making this interaction between these 2 carbons and pulling them closer to each other than a single bond, this interaction between the pi bonds is going to affect the hydrogen attached to each of these carbons. So the more pi bonds you have between 2 central atoms, the hydrogens are going to be pulled more into the central atom as well. So the hydrogen number 4 is pulled closer to the carbon because the carbon has already, besides a sigma bond, it has 2 other pi bonds, which is making it closer to the carbon, to the other carbon, but also pulls the hydrogen that is already attached to it. Now we go with the number 2. As you see, the number 2 is a single bond between the hydrogen and the carbon. However, the carbon has a double bond with another carbon. That means besides a sigma bond, there is a pi bond that is pulling these 2 carbons together. But not as much as a triple bond, but of course more than a single bond. So the pi bond between these 2 carbons is pulling the hydrogen more toward the carbon. And as you see, we're going to be left with the bond number 3 and bond number 1. The carbon that these 2 hydrogens are attached to, they all have single bonds around them. So basically the length of these 2 are exactly equal, and they're going to be the longest bonds in our question. So as you see, as always, you should know that from General Chemistry 1, but I'm going to say it again for you. The single bond is the longest bond always because it's just a sigma bond. The double bond is shorter than a single bond because there's also a pi bond besides a sigma bond that is pulling these 2 with a side-by-side overlap. And the shortest bond that we have is a triple bond because we have 1 sigma bond and 2 pi bonds trying to drag these 2 atoms closer to each other. Okay, let's see this example. You see here we have 4 carbons in our main chain, 1 double bond and 1 triple bond. The rest are single bonds. So the bond number 1 and 3 and 2 are identified for us. Now, as always, we're going to identify the pi bonds. As you see, as I told you, double bond has 1 pi bond, triple bond has 2 pi bonds. We identified that with blue. And now we're going to go with the hybridization of central atoms. Hydrogen doesn't need hybridization because it is always S. As you see, the first 2 carbons, they are sp2, and the last 2 are sp because they have a triple bond and they only have 2 sigma bonds each of them. As I said in the previous question, if you have a single bond, attached to a central atom that has another triple bond on the other side. That means it has two pi bonds with another central atom. At the same time, it is pulling the atom that is attached to it with a single bond. So this hydrogen on number 1, as you see, is attached to a carbon that has a triple bond on the other side. So the two pi bonds is not only make these two carbons to be closer to each other, but also it is pulling the hydrogen toward the carbon. So bond number 1 is the shortest. As you see, the bond number 2 and 3 are both single bonds attached to carbons. Both of them, they have a double bond. Now it doesn't matter that these two carbons are attached to each other with a double bond. They could have been attached to different carbons with a double bond. But since these carbons both have a double bond, these hydrogens are going to have the same length because there's only one pi bond trying to drag these two carbons to each other, and that affects these two hydrogens as well. So the third example, we're going to go with CH3, NH, CH3, CH2, and double bond CH, CH3. Now as you see, they already drew the Lewis structure for us, and we have only one double bond, so that means we have one pi bond in that and one sigma bond. Okay, so now we're going to go with identifying the hybridization of each atom. So the first carbon on the far left, as you see, it is sp3 because it has 4 sigma bonds. Now it gets tricky here. The nitrogen has only 3 sigma bonds, but because it has a lone pair on top, we're going to consider the lone pair to act as a sigma bond. So it is not a bond, but in hybridization, we're going to consider it sp3. So for example, if you have an oxygen with 2 single bonds, it already has 2 sigma bonds, and it already has 2 lone pairs. So we're going to consider those 2 lone pairs to act as a sigma bond. They're not going to act, but we're going to consider it like that. So it's going to be sp3. The third atom, which is the carbon, is going to be sp3 again because it has all single bonds. Same story with the fourth one. Now, the second nitrogen, as you see here, it has one single bond on the left side and a double bond on the right side. So, as I said, one of those bonds is considered a pi bond. Now, 2 sigma bonds plus the lone pair is going to be sp2. Again, as you remember from the previous examples, the carbon with double bond and 2 single bonds is considered to be sp2. And the last carbon, since it has 4 single bonds, it is considered sp3.